You've seen a game of pool, and you've probably seen footage of a car crash. I mean, they're both collisions, right? Things hitting each other. But in the world of physics, they couldn't be more different. And it turns out, understanding that difference, well, it could actually save your life. So let's get into it.
So to get us started, here's a little puzzle. Imagine two identical cars hitting a solid wall at the exact same speed. Car number 1 is built to be super bouncy, like a giant rubber ball. It hits the wall and springs right back. Car number 2 is designed to crumple like a soda can. Which one would you rather be in? Now, your gut might tell you one thing, but physics might say something else. And by the end of this, you'll know exactly why.
You know, when we think about collisions, we think of pure chaos, right? Just a mess of flying parts. But underneath all that chaos, there is one single fundamental law of physics that is never, ever broken. It holds true for every single collision in the universe. And that law is all built around this one idea, momentum. Now, momentum isn't just about speed. It's what you might call oomph. It's an object's mass times its velocity. Think about it. A bowling ball and a tennis ball coming at you at the same speed. You know which one has more oomph. And here's the crucial part. Direction matters a lot. Which way something is going is just as important as how fast it's going. And here it is, the big one. The unbreakable rule is the law of conservation of momentum. And all it says is this: in any collision, the total amount of momentum you start with is the exact same amount of momentum you end with. It can get transferred between objects, but the total never changes. It never just disappears. This idea is our foundation for everything.
Okay, so that leads to a pretty obvious question. If every single collision follows this one exact same rule, then why aren't all collisions the same? What's the secret ingredient that makes a clean bounce so different from a messy crunch?
The answer is another quantity you've probably heard of: kinetic energy. This is the energy an object has simply because it's moving. And even though it sounds kind of like momentum, here's the twist. Unlike momentum, kinetic energy is not always conserved in a collision. And that one fact, that changes everything. So let's just put them side by side to make it super clear. Momentum has direction and is always conserved, no exceptions. Kinetic energy has no direction and is only sometimes conserved. And that little word, sometimes, that's the whole ballgame. That's the dividing line between different types of collisions. So this critical difference splits the entire world of collisions into two main categories. I like to think of them as the perfect bounce versus the real-world mess. Let's break them down. So on one hand, you have what physicists call an elastic collision. Think about billiard balls. They smack into each other and rebound perfectly, super clean. On the other hand, you've got inelastic collisions. This is where things get deformed, they might stick together, things just get messy. First up, let's talk about that perfect bounce. In a perfectly elastic collision, not only is momentum conserved, because, it always is, but the total kinetic energy is conserved too. All the energy of motion that the objects had before they hit is still there right after they hit. It's the cleanest possible interaction. Now, I gotta be honest, in our big everyday world, a perfectly elastic collision is basically a theoretical idea. But we see things that get super, super close all the time. The sharp crack of billiard balls, air molecules bouncing around in this room, and of course that classic desk toy, the Newton's cradle. The whole reason it works is that those little steel balls have nearly perfect elastic collisions. Okay, now for the real world, for the messy stuff. In an inelastic collision, momentum is still conserved. That rule never breaks, remember? But kinetic energy is not. Some of that initial energy of motion just seems to vanish during the impact. This is by far the most common type of collision you see every day.
But hold on a second. I'm pretty sure we've all heard that energy can't be created or destroyed, right? So if the kinetic energy isn't conserved, if it's lost, where the heck does it go? It can't just puff out of existence.
Exactly. It doesn't disappear, it just transforms. It changes its form. That lost kinetic energy gets converted into other things we can actually see and hear and feel. It becomes the loud bang of the crash. It becomes heat. The bent metal literally gets warmer. And most importantly, it becomes the energy used to permanently bend and break the objects, the energy that actually crumples the car. And you can take this to its most extreme. That's called a perfectly inelastic collision. The easiest way to picture this is to imagine two lumps of clay hitting each other. They don't bounce at all, they just smoosh.
They stick together and move as one big lump. That's when you lose the maximum amount of kinetic energy possible. Okay, so we've got the perfect bounce and the messy crunch. We know momentum is always conserved, but kinetic energy is the variable. Now let's take all of that physics and use it to finally solve our puzzle about the car crash.
And here it is, the big idea. The entire point of a modern car's crumple zones, the front and back of the car, is to force it to have a messy, inelastic collision. It's not a design flaw that they break apart. It's an incredibly clever, life-saving feature. They're designed to be messy. So why on earth would you want a messy crash? Well, the thing that hurts you isn't the speed. It's how quickly you stop. It's that sudden jolt. By making the car crumple, engineers are actually increasing the amount of time the crash takes. Instead of an instant hard stop, the car spends precious milliseconds bending and folding, and stretching out that time, even by a tiny fraction of a second, massively reduces the force that hits your body. Let's look at the actual physics. The crumpling inelastic car has to go from full speed down to zero. That's a big change in momentum. But the bouncy car, oh, it has it way worse. It doesn't just stop. It has to go from full speed to zero, and then get thrown all the way back to full speed in the opposite direction. It experiences literally double the change in momentum. And there's our answer. A bigger change in momentum means a bigger and much more dangerous force being exerted on you. Since that bouncy, elastic car delivers twice the change in momentum, it hits you with a way more violent force. So the messy, inelastic, crumpling car is, without question, the safer car. You know, physicists don't just like to have two boxes for this. They put it on a scale. It's called the coefficient of restitution, or just E for short. And it's really just a simple number from 0 to 1 that gives any collision a bounciness score. And the scale is super simple. If E equals 1, it's a perfectly elastic collision, our perfect bounce. If E equals 0, it's perfectly inelastic. That's the two lumps of clay sticking together. And just about every collision in the real world, from a basketball hitting the floor to a fender bender, is somewhere in between 0 and 1. So here's a final thought to take with you. Bounciness isn't really a property of just one object, is it? It's a property of the interaction between two objects. A super ball is only super on a hard floor. Drop it on a pillow, and it's a dud. Which kind of makes you wonder, what other things in the world that we think of as fixed properties of a single object are really just relationships in disguise? Something to chew on.